y, z, and t as well. Now, using the second function because this might not necessarily be the same function. The law governing the velocity along the x direction, which is u, might not be the same as that governing it along the y direction. So similarly, w is equal to a third function of x, y, z, and t. So this in mind, we proceed to generate, because this is usually the basis of Eulerian method. So you start from the velocity and then you define other parameters. You start from the individual velocity components. Like I told you, this is the velocity component in the x direction, in the y direction, and in the z direction. So let's start. How do we get the accelerations now? Now, if you have a velocity in the x direction, definitely you should have an acceleration in the x direction, right? So we'll look for the acceleration in the x direction. So that's what we want to do now. So look for acceleration in the x direction, the y direction, and the z direction. So the acceleration in the x direction is usually denoted as acceleration sub x or a sub x, right? And that would be equal to partial derivative of the velocity in the x direction divided by time, right? We'll get to this later on, but then let's look at the mathematical aspect or concept connecting this. So how do we get the velocity, sorry, the acceleration in the x direction? This is a focus for now. So how do we do that? We take the change, or the change in the value of u, or the velocity component u. So the change in the value of u denoted by du is from your basic calculus. If you still remember, or from partial introduction to partial derivatives, you should know that it's change in a variable that depends on two or three other variables is denoted by this partial derivative, and they call this, in some cases they call this total differential. So total differential of u du is equal to the partial derivative of u with respect to x multiplied by x, then sorry, multiplied by dx, plus the partial derivative of u with respect to y multiplied by dy, plus the partial derivative of u with respect to z multiplied by dz, plus the partial derivative of u with respect to t multiplied by dt. So this is the total derivative, or the formula for the change in the value of u. So remember, we are looking for the change in the value of u divided by change in time, or the acceleration in the x component or x direction. So that would be equal to change in u divided by change in t. That means you divide every term here. That's I'm dividing here by dt, here by dt, here by dt. That you divide all through by dt. So if you do that, you get partial derivative of u with respect to x dot multiplied by dx over dt. That I've divided here by dt. So instead, I just divided and rearranged so that we don't prolong our work. Otherwise, I'll just say divided by dt, and then I'll have to rearrange. So I'll do the same thing for the next term. Partial derivative of u with respect to y dot dy by dt, plus partial derivative of u with respect to z dot dz by dt, plus partial derivative of u with respect to t dot dt by dt, right? So we have this. So from here we'd get partial derivative of the u with respect to x dot all this. Now I want to bring your attention to something. The x is actually the displacement in the x direction, and then we know that the rate of change of displacement in the x direction will give the velocity in the x direction, right? So what I'm saying in essence is that your dx by dt is equal to the velocity in the x direction, which is what? U. Your dy by dt is equal to the velocity in the y direction, which is equal to what? V. Your dz by dt is equal to the velocity in the u direction, which is equal to w. And then dt and over dt is 1. As you know, if you differentiate t with respect to t, you get 1. So what we'll do now is our du, this is the partial derivative actually, du by dt is equal to du by dx, that's partial derivative of u with respect to x, then dot, we already know that dx by dt, just like I explained, is equal to u. Why is that so? just like the rate of change of displacement with respect to time, displacement in which direction, in the x direction. So that's why it's denoted by the velocity in the x direction, because we know that the rate of change of displacement with time gives us what? Velocity. So that will be that, plus the second term will be du by dy dot the rate of change of velocity, sorry, displacement with respect to the y direction is v, because the velocity in the y direction is v, plus du by dz dot dz dt, you know, is w, plus here you'll be left with just du by dt, right? So this is our velocity, sorry, this should be ordinary derivative du by dt, and we know that du by dt is the acceleration in the x direction. So this is ordinary derivatives, please. This is not partial, because otherwise you have a conflicting partial derivative term here. So from here you get du by dt to be equal to this, and we know that du by dt from here is equal to acceleration in the x direction, and that will be du by dx dot u plus du by dy dot v plus du by dz dot w plus du by dt, right? So this is the acceleration in the x direction. So similarly, acceleration in the y direction, similar